So like introductions, I'm Scott McMahon. I'm a solutions architect or senior solutions architect, sometimes called a solutions engineer, depending on what year it is with Hazelcast. As he said, we primarily, I guess I'll talk about this a little bit, but we're primarily known for the caching technology, our distributed data grid and some of the enabling technologies around there. But it became apparent about 3 years ago that there was a need for the processing engine to layer on top of the data grid to handle the event streaming and distributed calculations and aggregations and things like that. That's where Hazelcast Jett came along. So we are at 0.7, which was almost our 1.0 release. We've been working on it for about 3 years. What I'm told is in December will be our 0.8, but that will actually be our 1.0 GA release. We have several of our larger customers that are actually running in production with it, and we support them, and that's some of our test cases. So it's we spend a lot of time getting it right, and then we're just now starting to kind of roll it out to the general public. So that's really kind of how it came about. So today, we're really going to talk about, if it'll switch, maybe I need to click. Oh, it went too fast. The stream processing. So that's really at the core of what Jett is for. Can you hear me? Is this working or should I just talk? Okay. You know, the Jett layer is all about being a real-time, single event-based streaming engine. I need to put my glasses on. So, sorry, this thing is jumping around a little bit on me. So it's really about, the first thing to start talking about is what do we mean when we start talking about, you know, stream processing? What exactly is it? Because as we start to look at how we process information, especially coming in and out of our data grid, we kind of run into these three buckets. And there's sort of your online systems where you have that request response. You know, it's low latency, but it's also small volumes, and it's not really what we mean when we start talking about streaming. But then, you know, after that, we start talking about batch processing, and this is historically, I'm sure everybody has been involved with various flavors of batch processing. And that can be actually a little bit later. What we'll talk about is how you use some of those finite batch data sets to actually enrich what is your infinite data stream as it's coming through the system. So then that gets us down to true stream processing, and where that's really defined is around the context that it's an infinite stream. It's not going to stop. So with a batch job, you have a start, you have a stop, you know, a beginning and an end, and you know how you can process that. But when you have an infinite stream of events, that starts to open up new opportunities as well as new challenges as to how you do the calculations, how you do things like aggregations, you know, across, and that's where we'll talk about the concepts of windowing and some of the different things that you have to do to process a stream. The reason for it, and one of the things that occurred to me a while back is that you can actually think of a batch job as a stream if it's done every day. So if you have a daily batch of processing that you do, you could think of that as actually as a data stream. It just has really high latency. The latency of that is one whole day before you get your answers. So what we start to talk about with true real-time streaming is where you reduce that latency down to, you know, right now. And a lot of people use the real-time term, but I learned a long time ago, there's really no such thing as real-time, but there's kind of perceptual real-time. So we'll say real-time knowing that we really don't mean exactly real-time. And also the volume, you know, today's volumes, like this is what's driving this streaming approach. It's not only do we have these endless streams of data that are coming through, but in the traditional sense, you would want to store them into a database or drop them in and then kind of run some analytics. But the things that are generating data now from mobile to the IoT use cases along those lines, there's just too much data and there's really not any value of storing it. Back when I was doing Hadoop, I would have told you the opposite. I would have told you need to store everything and buy more nodes to do it. So but it's really not true. So, you know, processing on the fly lowers that latency, and it also reduces your data requirements. So what I'm doing here, I'm just a little bit of setup. Sometimes this gets a little boring, especially when I've said it a few times. But you really want to talk about, where this fits in, and then a little bit of the history about how it came up. And I do have a demo that will show, and some code samples, and we can step through that and talk about how it works. As a quick question, am I allowed to ask questions? I don't know if it's not going to be on film. Who here uses much of the streaming, the Java streaming API from Java 8? Is anyone familiar with that? Yeah, kind of. Because the way we built it, like Hazelcast from the beginning, we've always tried to stay easy to use. So even with our original data grid, we just really extended the Java util, map classes and the Java util classes. So if you're used to using a hash map or something, you set up a cluster, and with a couple of lines of code, you get an IMAP, which is an implementation of a hash map, but it's in the cluster. After that, you use it the same way. So with Jett, we did the same thing. We really, for the most part, just extended the Java concurrent streams, I think it's concurrent streams, API, so that if you're used to using that, and the way that chains up and the new functional Lambda stuff that came with 8, we really built on top of that. So as soon as if you're used to using that, or you want to get used to using that, then this code that you see from Jett will really feel natural and look natural, and it behaves in exactly the same way. So from here, when to use stream processing, I think most of us probably know that. Probably right now, the biggest ones we see are financial industry fraud, trading, needing to do super fast analytics on an individual, like a stock price or commodities price, or, a lot of the financial institutions are, at card swipe, they need to send that in, run it through the fraud algorithms, and then give back a yes or no on the transaction. And we've gotten that, I say we play a part in it, we don't do it all, but that's down to, it used to be 30 or 45 seconds just a few years ago, and now it's down to just maybe a couple seconds. And each piece, we participated in a lot of that, especially at the data grid level. We get things down to 4 or 5 milliseconds in our little part anyway. But that's where we're seeing it. And then obviously, like I already said, the continuous data is just wherever you have an event stream that's coming through, and you want to be able to look at each individual, event as it comes through the system. And these aren't actually my slides, so I have to read them a little bit sometimes. But and this is really kind of going back to what I was already saying about extending the Streams API. It's like, what does it do for you? What does a real-time processing and event processing do for you? It's really around, right now, not really analytics, the aggregation, the mathematical functions. Like it says up here, when you map something over, you do transformations on the fly of each event as it comes through the system, or you start to do the aggregations and the group bys, and that's where you get into being able to look at things like averages and means and standard deviations and things like that as these things come through your system. So that's what it really gives you, and that's on a per event basis. In the past, you would have to kind of run more of a batch. You would get those events, store them probably in HDFS, and then run some kind of a batch job to figure that out. But it's always a little bit latency, depending on how fast you can run your batches. So we're doing it now immediately as soon as that event hits the system. So, and the other part of what we've done too, it was never hard to get data into IMDG, into the data grid. But with all these new I say new, Kafka's been around for a while, but Kafka's sort of taken over. But with all these new sort of sources and sinks, as we'll see later, we treat them, there's just so many different data sources. We needed to make that more modular. So Jett also gives us that ingest and whatever is the opposite of ingest, the piece of it. So you implement your data pipeline and submit it. It runs across the cluster. It's all distributed, fault tolerant, all the things you would expect. So real quick, just sometimes I think I get questions about, why are we doing this, and where did it come from, and what's the job? So real quickly, I like to at least kind of go through the evolution of how we got there. I'm sure many of you remember ESBs. I think they're still around, probably. I remember when that was the new thing. But that was sort of the first time we started looking at an event-driven architecture or a message-driven architecture, and that whole decoupling of the applications. But it really wasn't, there wasn't enough data sources to do real true streaming, and the buses really weren't fast enough because they didn't have the clustering. They were usually backed by either a file system or a database, and it wasn't really built for that. It worked well for pub sub architecture, but it didn't really bring the opportunity to do true sort of stream-based processing yet. But as they got faster and they got better, that's where we started doing the CEP, complex event processing. But that's still not truly like stream analytics. It's not, it doesn't do the complex computation. It's really just you predefine patterns of events that you're looking for that might indicate something is happening, and you submit that to the stream that's running. And TIBCO was good at that. Actually, I don't have web methods up there. They were pretty good at that. And it's just looking for those patterns. And when it finds that pattern or it hits that sort of, that thing you're looking for, it'll just emit another event, which is what the complex event, that's what the thing is for. But again, that's not analytics. That's just sort of predefined things that you're looking for, and you have to already know about it, and then you react to it. It's reactive. It doesn't really give you much capabilities. Now, about that same time we were doing this, though, that's when machine learning and the data scientists started to kind of emerge, and they started building models. And the idea was, can we build like a self-training model? I think they call it unmoderate mod, something like that. I don't know. They have trained and untrained, but they started trying to figure out, how do we build these things on the fly instead of having to know how to do it and write a query essentially and submit it to the system. Now we want to build ourselves. So that was starting to come along, and then at the same time, Hadoop came along. And my coworkers, I don't always agree with them, tend to think that Hadoop and MapReduce was sort of the first generation when we started to look at actual sort of per event, processing. But to me, in my mind, it was still somewhat batch, because all you were really doing was taking these individual events, and this is also when kind of, unstructured data and NoSQL was coming out. You're just basically dumping all these individual events into a data store, and then you're running MapReduce to do aggregations, or the famous word count and all that stuff, which we're going to see the word count here shortly. So, but it still ran in kind of a batch mode. It still wasn't really event processing, but it was the first time we really started to look at these big data sets. And the ecosystem was quite large as well. But MapReduce was clunky. You had to chain together all these things. You had all these intermediate steps where it had to store data to basically down to the hard drives, because it really was a file-based system. And every time you had to do that, you had to write another MapReduce job and kind of work through this whole thing. And it was really hard to use. So that's where the idea of Spark came along. And it says UC Berkeley, and it really was, but it was Databricks that came out of Berkeley and built it. But that was the first idea where we said, okay, we've got these big data stores. We've got this distributed system, and Hadoop being and HDFS being made up as these different nodes. You could now, it was the first time you could say, all right, well, not the first time, but it's the first time the general public would say, all right, now we can do distributed processing, and you can write some kind of execution, and it'll run out on all the nodes and take advantage of parallel processing and then reassemble and come back. And by the way, you could do it in Java, and you could bring in other Java libraries, and you could do whatever kind of computation you want to do. So that started to open up the whole field of it and give that sort of freedom. And then, machine learning was coming along, and AI is not far behind, and you could plug that in. You could train your model on the data that you had, and then you plug it into your Spark job, and Spark would feed it, and it would spit out its results. And that was really cool. However, it's still very slow because it's based on Hadoop, and Hadoop is a bunch of disks all spinning together, and you have that sort of disk latency. You have that distributed part. And HDFS, it really hasn't changed too much since the beginning. So it kind of was still lagging. It was also more or less batch oriented. You ran your Spark job, and you could run it a lot and shorten that window down, but you were still batch and kind of having to deal with that latency. So that's where the next thing came along, was Spark streaming. And all Spark streaming actually is just running a micro batch in a loop. So you run it really fast and your batch just gets smaller and smaller, but it's still not truly event-based. They try to fake it and shrink it down to as small of a window as you can get, but you're still doing it in batch, and you're still having an application that has to go over each one. It's kind of funny, as a little side note, Spark kept trying to get faster and faster in their batch and micro batch and all this, so they could say that they're Spark streaming. And for us, the first thing we ran into is we're actually true streaming on a single event basis, but people were asking us, well, can't you just do it in batch? Like, I don't want to do every one of them. So we have to kind of fake batches to satisfy people that want small batches, but you know, it's just a batch of one, I guess. So anyway, that Spark streaming came along, and that's kind of what we think of as sort of the second generation of event-based sort of processing or stream processing. So then we start thinking of ourselves as the third generation, and this is where we truly start to run in memory, single event. You have the capacity and the capability to receive an event and be able to do these complex aggregations and these things that you need to do and keep up with it, but do it for every single individual one. And also be able to sort of mix maybe, other, we call it a batch, but it's really data in a map. We just treat it as a batch. Be able to enrich streams or enrich, your data sets and do these calculations and aggregations. So, if anyone's familiar with Spark and some of the other ones, Storm and Flink are also DAG-based, and I'll talk about that in just a second, but that's just sort of, it's a concept of how you do the execution that lends itself to being able to be on a distributed environment. So Spark did it, and that's why Scala came along, because Scala was built, it's just a subset on top of Java, but it was built so that it would force the programmers to write code in a way that was easily distributed, because you can do things without knowing it, and with distributed capabilities, especially with Spark. Like, you can use Java, but if you do something like, if an int is 1 and loop over something for 100, and you try to distribute that, you've actually just ruined your distributed calculations, because it's got to coordinate that one int value. It's got to say, like, I'm 3 and you're 2, and is it still 2? No, it's 5. And it's got to do that sequentially. So there's really simple things you can do that just kill your application as far as taking advantage of the performance of the distribution. So that's where Scala came along. But even so, it's you're still kind of working in the HDFS. A lot of what Spark does is sort of to get over the latency of the disk and the system. But what they did come up with was a really good idea, and that's the DAG-based thing, where you can break up your process into these subsets, or we'll call them, their edges and vertices, and the actual processing is on the vertice, and it can be executed anywhere. So that's how it really lends itself well to the distributed fashion. And then what we'll see too is when you stick it on top of the in-memory data grid that we have, all of a sudden you can use those as buffers in between the steps, which really sort of unlinks everything and allows it all to run in parallel. So that brings us to Hazelcast Jett. And I know I really try not, it's not a sales pitch like Jason said, but I do work for Hazelcast, and these decks are made kind of, a lot of them I pick and choose, but they are kind of developed by marketers. So they kind of sound salesy, but that's not what I'm trying to do. But Hazelcast Jett is our distributed computation engine. It is built on top of IMDG. And when I say that, it's a little confusing at first, because you think, oh, I got to install this data grid, then I got to install, Jett on top of it and deal with all these things. It's actually, we built, IMDG is a very mature, distributed, capable product. All we did was we basically OEM'd our own product inside of Jett. So you just started a Jett node, and it has all these capabilities, and you don't have to see that, or you don't have to deal with the low-level stuff, but it actually is using IMDG inside of it for all the distributed calculation and the resiliency and all the things that come along with that. So it's built on IMDG, which also, by the way, puts all the data in memory. So we don't have any disk-based stuff. Everything's already available in memory. And if you're interested in IMDG, one of the things that's really cool from a Java side is that we built in, it's just a flip of a switch. You can actually allocate memory from the hardware outside of the JVM. So it's not part of the heap and it's not subject to garbage collection. So we do that here. So each node can have a higher density. Like if you're just going to be in a JVM with standard on heap, I mean, you probably don't, 8 gigs, maybe 10 gigs. I've seen 12, but you're kind of getting to where you're just going to hit too much garbage collection. But once you move that off heap, then you can have a much higher density. So we'll have individual nodes of the cluster, whether they're HDF or IMDG or Jett, probably 50 gigs a piece that it can handle storing that data, and that's all in RAM and all directly accessed. We use the C libraries to hook into that, but you don't have to worry about it. So, what is this? This is kind of standard IMDG stuff. So like I said before, we always try to make it easy for a Java developer to use. So we extended the concurrent map or the hash map or the Java util map thing. So when you wanted to use Hazelcast IMDG, really all you have to do is that one statement where it's a Hazelcast, it's a single jar, it's about an 8 meg jar, you include it in your application, that's all you do, there's no dependencies outside of it. You don't need anything. You can hook other things in, like Log4j, which I would suggest, but you don't need to. But all you do, statically grab new Hazelcast instance, and when that gets created, that's actually a node. That's now a Hazelcast IMDG node. It's as simple as that. Then when you want to get a map, instead of just saying new distributed map or a hash map, you just say acyclic map. And there's a little configuration. That's the name of it you give to match its configuration. That's what it's going to be called in the cluster. But then you have this map. And it's a concurrent map implementation. So the rest of it, you just use it as if it's a regular old Java, concurrent map or hash map or whatever you use. So we do that to make it really easy as a developer to use it. And what you'll see is on a later slide, I guess, the Jett code is the same way. It's the same thing as using streams. You just say, give me Jett, give me a new instance. And then you say, instance, give me a new pipeline. And then from there, it's map and aggregate and those things that you would normally do. And then you drain to a source or a sink. And then, Bob's your uncle, as a guy used to say, I know. So, with IMDG, we have these different data structures. I guess there's a stack slide here, so I'll go over it. But there's some pretty advanced structures you can use. IMAP being a map implementation is probably the most common. And it has a lot of stuff like distributed. We have concurrent executors where you can write distributed applications, entry listeners, and entry processors, and all kinds of distributed processing stuff. And that's what Jett actually makes use of under the covers a lot of the time. So we had to build new stuff for Jett, but when it can, it uses that mature code that's already there in the data grid that's incorporated in it. And then there's distributed versions of these atomic longs and countdown latches and semaphores and things like that. That's all pretty standard IMDG stuff. And here's the stack. I'll quickly go through this. Basically, we don't really care about the underlying platform. It just needs a good JVM. As long as we've got a good JVM to run on, and we run on most of the accepted ones, that's fine. Don't worry about the blue stuff. We just consider it on heap. Really, the engine part is what we've developed over the last 10 to 12 years, and that's on the IMDG data grid side. That's all kind of done for you. That's the memory partitioning and the distribution and the replication and failover and all that kind of stuff. That's all done for you. As a developer, you use those objects up in the API. So in your code, after you create an instance, you say, give me a map or give me a multi-map or give me a set or a queue or a topic. The queues and topics are implemented the same. They kind of follow the JMS pattern, but it's we're not a JMS provider, but if you already are connected to this, you can use that same as a JMS kind of queue and topic. And then on top of that, we actually have clients. We've implemented that open client network protocol, which is basically just a generic protocol to interact with the cache. So we can build all those clients natively in their language. So the application's Java, and our Java client is probably, or will be, and continue to be our most mature. But when you have a cluster up and running and you have applications in these other languages, you can actually interact with the cluster itself. So going to Jett, sorry for the big thing, but all of this IMDG stuff and all of that on the bottom is the same. It's just built on top of that. So when you see core, that's where we built, I call kind of this stuff the IMDG stuff, the engine, that's the IMDG engine. Now we've built that core. That's basically the Jett engine. That sounds funny, but that's the engine part. You don't have to worry about it. It's built for you. You don't, I mean, built already, but that's what's going on under the scenes when you submit a job. You create a cluster, you create a node joins a cluster, they form a cluster. All that happens automatically. You submit a job to it and it runs. Up there, you know, in the high-level APIs and connectors, that's where as a developer, you start to lay out what is your pipeline, what is your process that you're trying to model, and what are you going to run. And then once you submit it to the job or to the cluster, that job will be compiled down and built into an actual DAG, and then the DAG gets executed on the cluster, right? And then, you know, you can also use the clients because there's still that open client protocol. And I do have some code and we've got some demos, so I think it'll be a little more clear when I go through that. But really, that's how it works. So, and also again, it's a single jar for Jett. It's, I think the IMDG is about 8 megs. The Jett jar is about 9 because 8 of it's IMDG. So we've added a little bit, but there's no dependencies. You can get it from Maven or Gradle or whatever, or just download it and stick it in your class path, and you can use all of this stuff and it will run. Now I say that, and it is simple because out of the box it takes all of the default kind of settings, but there is also a whole lot of configuration stuff you can start to play around with to do specific things you want to do. But we do our best to try and kind of set what would be normal parameters for a general kind of installation. So you can go download it. It's all open source too, by the way. All the orange stuff is open source. The blue stuff is what we charge for. And the idea really being, number one, we have to make money somehow. So, you know, we have to, we're a subscription, so we charge for it. But as a developer, and even a development team or prototyping or a small developer, all that orange stuff is open source, and that's what you can get and use for free. I forget the license, probably just the GPL license, and it's fully functional. There's no hamstrings, there's no limitations on it. It runs exactly as the enterprise. All we do is figure, you know what, when the big companies start getting it and they start implementing big projects, they're going to need security and they're going to need, you know, rolling upgrades and failover and active data center clustering and all that kind of stuff. So that's when we say, okay, you got to pay for that. But as a developer, you're free to use it and develop and use it however you want. A lot of the projects actually OEM. I used to have a slide that shows all the OEM projects that have IMDG embedded in it because all that clustering and all that sharing and all that distributed processing is done for you, so you don't have to reinvent it. So we're a part of some of the really good, you know, open source projects that embed us and OEM us. Oh yeah, well it's 10 megs. Sorry, I said 9. So you know, here's Hazelcast Jett. So it's built on IMDG. So, and that second line is important because, like I said, there's still batch out there, but we actually treat the idea of batch a little differently. We treat it like a stream, but it's actually just a stream that has a beginning and an end. You know when it starts and you know when it stops, so it's a lot easier to deal with. What we really do with it is we just take that data source, depending on how big it is, and load it into a map under the covers. And then when that stream is coming through, your real unbounded stream, we can actually just do a correlation and a join on what's in those streams that are already in memory. And that's how we do enrichment. We do stream joins and some of those things. Now we can join live streams too, but you know, when you start talking about most of the time, your jobs, you'll have your live stream running, and it's something that you're interested in looking at. But the things that you compare it to and the things that you start to give you the information to make decisions are usually kind of static. You know, they may change a little bit, but which we can handle. But usually it's kind of a set and known thing. You're just trying to figure out what to do with these streaming events. Yeah, so we started in 15. Yeah, minimum Java JDK 8 because the streams. I mean, we've implemented the streams API, so you got to be using Java 8 or whatever version. So I know I'm talking fast. Should I ask for questions? I don't know. I'm actually pretty interactive, so if someone, I don't mind being interrupted. So if someone has a question, you know, just speak. What'd you say? Configuration? How much configuration? You mean talking about integrating with Hadoop or just in general? Okay. So with Hadoop, we would use a connector, right? So you would start, you'd have a Jett cluster and it would be running and you have that whole thing, but your data source would probably be HDFS. So we can actually, you just configure the HDFS connector basically, and it uses it as a source. And from the Jett perspective, from IMDG perspective, it's a connector. From Jett perspective, it's a source or a sink. And all you do is configure that. There's out of the box sort of templates and static methods to create it. So you just say, you know, there's a utility class called sources, and there's a utility class called sinks. And you would say, you know, it's a factory, and just give me an HDFS connection, and you give it, I think you give it the URL and the file, you know, because it's file based, you get a file path and maybe your credentials, stuff like that. We can tie into LDAP and Active Directory, but Hadoop, you know, you just usually give it your credentials. But then it just treats it as a source and a sink, with the understanding that HDFS is immutable, so you know you can't change it. So when you're reading and writing, there's little tricks you have to do under that. When we're dealing with in-memory data structures, we have full, you know, access to it, and we can read and write and update. So, but you know, it's just another source. In fact, that's what this next slide is. I guess that's good timing. So, I mean, all of that ingest and output, it's just a source and it's a sink, and you just connect to it, and the connection is built into, you know, what we've built for you. So you really don't have to worry about the implementation. It's just configuration, and there's not much to it. And then from your code, you just treat it. You just, you know, you create a pipeline, and then you say draw from, and you get all these events, and it will take, even if it's on HDFS, you know, depending on what it is, HDFS, depending on the data structure, it's probably a line by line kind of thing. So it will read each line and treat that as an event, and then you can map it into a job object if you want, or something, you know, along those lines, like a message event. But it will treat that file, which is what it really is, as a data source, and you can append to that file, and it'll continue, it'll watch it, and then you can sort of continuously process what lands into HDFS. But I would say by far, the most common one is the one at the top is Kafka, because everybody that's using Hadoop has probably got Kafka running. So we can just, you know, that was the first one that we implemented, and you can read and write directly from Kafka. So it's just configuration of that stream. There's one in here where the demonstration app that I have, it actually reads the flight information from, there's like a national clearinghouse that tells you all about, I didn't know they had this, and it seems kind of, I don't know, it seems unsecure to me, but you can read all of the flights in the air. It'll tell you where the planes are and whether they're going up or down and all the different things. And we actually take that and use enrichment to figure out if they're going up or down and where they are. You can get a lat long and tell where it is if it's near an airport. And we calculate kind of the noise level and the CO2 emissions from those planes. And it's actually running right now in the background. But so yeah, by far the fastest source and sync is the map, the IMAP, because that's a RAM, you know, it's a RAM-based structure, and it's right there. So I think there's a few slides in here that talk about comparing it to the other stream-based, you know, stream processing engines. And I know everybody's got their own benchmarks that say they're the fastest, but we really do try and give, you know, a fair shake and do testing. And sometimes we do it with a third party just to make sure. And so far what we've seen, and we haven't even done it in the last couple of versions, but Jett has been orders of magnitude faster than, you know, Spark and Flink and some of those other ones. So we're pretty happy with the performance. And that was really it. The one thing that we've always done at Hazelcast is that you kind of go in the beginning with, especially with the data grid, as they start to become mature, you got to sort of pick your direction, whether, because there's if you've ever heard of something called CAP theorem, and it's really just around, you know, being available as opposed to being consistent, because we're all partitioned. That's the P and the C and the A. You really can't do both. You can't have full availability and also do consistency across a partition cluster. It's just, it's a triangle, and one of them's got to give. It's, what was the old one where they said it's like you either have money or time or quality, and you can't have all three. It's the same thing with partition and consistent and available. So we always lean towards available, and what that means is performance. We always lean towards high performance. When you lean towards consistency, you're making performance trade-offs, because you got to do two-phase locks and all these kind of things. So we'll always, our whole mission in life is to be fast, easy, secure, and fast. I mean, that's really what we do. So with Jett, the whole point was to be fast, to process these events as they come in and do all the things we need to do and be able to do, you know, we have our financial customers doing close to 1 million transactions a second. So, you know, I mean, and so as far as we know, we're the only ones that can do that level. So, you know, I mean, so far it's working and we keep getting better. So I think I already said most of this. I think probably the interesting thing here is that third line where it really gets kind of screwy, if I can use that term, when you have to window, because like I said a few times, with a batch source or even a sync, you know when the start and you know when the end is. So you don't, if you're doing an aggregation, say, and you say, okay, I've got a million events. I'm just going to aggregate all of them, or, you know, get the average of all of them, or I'm going to do every 50,000 or something like that. When you have a continuous stream that's never going to end, you have to say, all right, I need a window. And what kind of window do I want? Does that window slide? Does it just jump and tumble? You know, I need a window, and I'm going to get these events out of order. So do I reassemble them? Do I put my own timestamps on them? Like, how do I know which events are in this window? And also, what if that window ended and then I get an event because it got held up that should have been in that window? Do I ignore it, or do I, you know, have to put it in my new one and recalculate? There's a number of different decisions you can make around that, and we've built in a bunch of stuff to handle that. And as always, the other thing on Hazelcast, whether it's IMDG or Jett, we build it in ways that we think make sense to use and that people are asking us for. And like, we have things called merge policies and the windows and all these different things you talk about. We build the ones that we think make the most sense. But ultimately, there's always an interface that you can implement yourself and build whatever custom function you want. So if you have some crazy idea for a processing window, have at it, and then submit it back to us, and we'll put it in the product if it's good, because it is open source. So DAG-based processing. What time is it? 10 to 11. I'm going to go through this and then we'll take a break. So what is DAG-based processing? It's really like cap theorem. It's a fancy term for something that's fairly simple, I mean, to me. It's basically a graph, but it's an acyclical graph because it doesn't ever have a loop. You always start at one side, and no matter what, you're going to go to the end, and you're never going to loop. So it's not going to have any cycles. And then it's directed because every vertex there has an edge coming out of it that tells you where to go. And it doesn't go to all of them like a true full-size graph would. It's going in the way that you build it. And to me, I think of that, I mean, I did a lot of BPM stuff back in the day, and I still think of it looks like a business process to me. And every step, every vertex is basically one execution part. So we'll find out later, I think it's in here, that actually once we implement that, those get distributed, and then every one of those has its own little executor thread that runs, and it's an independent little processing engine. But it knows the next step, and it knows the direction to go based on what the calculation is. So that's really all it is. And you take your process and you break it down to these steps, you build this thing, and then you submit it to the cluster, you submit it to the engine, and off it goes and it runs. And this is how Spark is built. This is how Tez and Flink, and I guess Storm. I don't think anybody uses Storm anymore, but sounds like they did it that way too. So I told you were going to see word count. The word, I mean, everybody wants to use the word count. It's pretty easy to understand. So if you have an incoming file, and it's, you know, it's a line. There's another. I should have brought that one. There's another demo where we do word count on the entire works of Shakespeare, the entire catalog, and that's actually available. And I have it just as a big text file. And it runs and it runs, and I mean, you hit the button and it's already done. It's just like, it goes real fast. So in this case, you just think of one file that's got lines, and lines have words. So you're gonna, you know, in the traditional sense, in a single threaded application, you go over the file, get every line, split every line into words, and then loop over every word and do your aggregation. And that's what we're gonna kind of start with. So that would be sort of, the idea how you would do it. But if you kind of think about it, you can start to see where you can break some of those things up. Like they're independent of each other. There's the thing about it, and the reason why this is a good example is because if you're just doing a word count, then the words don't really relate to each other. So you can just treat them as individual pieces of information, and all you're doing is counting them. So once you realize that, you can break them up into a stream of words and treat them independently. Now, if you're doing natural language processing and stuff, then you got to take them as bigger chunks. But for this one, we're just treating them each as a single word. So that's where you can start to think, all right, how am I going to break this up into what we would call a DAG? So all you really do is think about it. And this would be, if you did it in your traditional, loop within a loop, it's still the same thing. You're getting the words, you're breaking them up into words, and then you're sending them to some aggregator that's going to count each word and keep a running count. That's really all it's got to do, right? But how do you break that up? This is where it's easier, or it's convenient for us to be on IMDG, because we can actually take our in-memory maps and create what are essentially buffers in between each step. Once you do that, so you have, you read your source, you're putting a line in each one of these, this one tokenizes, it spits out the words, and then the aggregator either picks it up or it gets sent to the aggregator, does its job, and then it sends you out the results at the end. So you can see that it's already kind of built what we're going to refer to as a pipeline. So now that it's in that form and it's split into buffers, there's no reason why we can't take 2 of these tokenizers and say, all right, let's have 2, let's have 100 actually. We're just spitting out the words into these buffers, and each one is just going to process them as fast as they can. Along the same lines, there's no reason why we can't do the same thing with the aggregator. Now, if you're familiar with the word count, I'll show it maybe on the next slide. Okay, they do have this one. I thought they skipped it. If you look at this though, you'll find that you would have a lot of network traffic with this running back and through if you're having to send all these words to all these aggregators. So what we end up doing, if you think about it, this is a little bit of an optimization, is that because they're only word counts and this is a small job and we're distributed, and really what it gets at under the covers is that in the IMDG data grid, all of the data that's in that map has been distributed out on the cluster. And that's distributed based on a hash that's key, which means you get a general random there's other ways to do it, but you get a random distribution of the data out across the cluster. What that also means is that every tokenizer or every accumulator can run on its own little section of the data. It doesn't even have to go across the network. All it's got to do is read the partition that it's on, because every one of these tokenizers is also assigned to a partition. So there's no network traffic as this actually starts to happen. It's just going across each node. That's where we have added these combine elements, because then at the end, each one just sends out its totals, and the combiners combine the totals for whatever word that it's working on. So you only get one network piece of information for the entire job per node. Does that make sense? Sometimes that gets a little lost, but anyway, it all breaks up into these steps, and these steps are able to be executed independently. And then we can then say, all right, now let's add more nodes. And this is just where you get this full distributed, DAG-based processing that lends itself perfectly to running on a cluster and running in a distributed environment. And we can take advantage of parallel processing and do these jobs really, really fast. And we can scale linearly. So if you need more processing power, you just add more nodes to the cluster, and all of a sudden you've got more of these little edges and processors to do more parallel processing. And all the data will naturally be distributed out across them all, so they'll all just linearly increase your performance as that goes. I don't know why there's a second one. Oh, I guess it's just showing how it does that last step. So that's a quick kind of explanation as to how we do it. And then I think this is probably a good point to take a break. And then we can talk about a little performance, and then I'll show you that demo, and we can look at some of the actual code that runs it. Yeah. And if anybody has any questions, like I said, I'm totally open to questions. I may not know the answer, but I'll try. Yeah, go ahead. Yep, no, no, no. So there's two parts to that answer. He's asking me, look, so if we're AP and we're not consistent, how do we handle failure? So the idea behind that, the way we handled that, so in IMDG, the data grid, what we do is, like I've said, we manage partitions, and then every piece of data is assigned to a partition, right? But at the same time, every partition has a backup copy on another node. There's two reasons we do that. Number one is the node that is the primary for its, or the node, each node is a primary for the data that it holds in its partition. So when you go to get that data, the client, or however you're accessing it, is smart. I mean, the way we built it, it goes directly and accesses that data directly, right? There's only one node that has it. When you update it, you update that node. So any reads or writes that come along later get the new value. It's guaranteed because there's really only one value. But there is a copy on another node. So if that node goes down, the cluster knows it because there's heartbeats and health checks and statistics and all that. The backup copies immediately promote their copies, and they become primary for that data. So, and the cluster continues to run. That's one of the things from the beginning, is that we had to be resilient and not lose data and not go down, because there's going to be node failures. So, and we by default, we do one backup copy. You can actually make more depending on your level of redundancy that you need. One is usually enough. But then that promotes, it becomes immediately the server for that data, and then they redistribute the partitions and they redo their backups. And that's how we do it on that one. Now, so Jett is built on top of that. So Jett can take advantage of that part. What it also does is every process has the concept of a snapshot, and it's configurable about how you want to do it. So at certain points along the processing of each one of these jobs that you submit, you basically submit a DAG as a job to the cluster. It can take a snapshot, and in the event of a job failure, it can restart from any of those snapshots. If a node goes down, it actually will restart automatically from that last snapshot, and then the underlying resiliency of the IMDG grid takes over and kind of promotes and rebalances. So there's always scenarios where you can fail and lose data, but from a reasonably available type of thing, we've got enough redundancy built in that we haven't really seen a problem with that. And if we do, if it's some kind of information that just can't be lost, then we can add more backup copies, or we can do redundant clusters and have replication between the two. There's a number of different things you can do. And also, the grid can actually store its data down to some persistent store like a database or disk. But that lags a little bit because we have to do it in batch mode, because a database or a disk or anything like that will never keep up with the performance of the in-memory data grid. So, yeah. Mm-hmm. The metadata? Yeah, okay, right. So yeah, that's part of the snapshot. So it's kind of a complex thing, but actually what happens is all these events are streaming through, right? And you have to be careful of the order, and we do exactly once guarantees or at least once guarantees. There's a number of different things that we do, but each one of those, you kind of pay a performance penalty. But what we actually do in the stream is we insert a breakpoint, but it's called a breakpoint, in between the events. And then when that hits, it gets propagated out to every one of the nodes and every one of the vertices and all the jobs. And then each one of those gets that, and then it reports its state to kind of the master copy, which is also replicated. So that snapshot basically flows through the whole thing, and that state gets replicated over to that master copy. So that, and then when that's complete, that's the snapshot. So we know the values and we know the state of every one of these nodes that's running. And then if something goes down, the cluster reconfigures itself automatically, rebalances, sets itself back up, says I've lost a node, and hopefully notifies somebody. But then it will repartition, or it'll redistribute the data that it knows from the snapshot to the remaining nodes, and it will continue on from there as far as processing. You do pay, that's always a tricky one, because those snapshots, you pay a performance price for them. So you can say, okay, I want to do a snapshot at every step. It's like, well, you're gonna kill your performance. So you got to figure out, like, usually there's some natural spots where you can have a breakpoint, and say snap it here and snap it here. You don't have to do it at every step. That's also how we do scaling. So you can suspend a job and say stop and add a bunch of nodes to the cluster because it's not big enough to run this job. And then when you restart the job, the manager will say, oh, look, I've got new nodes, and it'll go distribute that out because it's using a lot of the partition management of the covers. And as soon as those new nodes join, from the beginning, it's already going to redistribute the partitions because the partition count stays the same, depending on when you set it. And then the system will know, oh, look, I've got these new nodes, and then it'll distribute the state data out across the new nodes, and then the job will continue with, as it was, but with all these new nodes. So you can expand dynamically, which is helpful on continuous jobs because sometimes they never stop. They just run. Like, I've got that thing running in the background. It's just running until I kill it. So you need things like that. Well, there's not a master node. See, that's what there is a node that is made the master of the state data, and then that data is replicated using that replication and failover stuff that's in the IMDG part. So, but in the general sense of things, we don't have a master node. They're all equal, so they all participate, and the data is totally distributed out, and each one is responsible for its own data. For the snapshotting itself, we had to get that in one spot, but then that's stored in a in-memory map, and then that is replicated to another node. So if the one goes down, this one immediately promotes its copy, which is exactly what IMDG does, becomes the master, and then will then replicate to another node to redo its backup. So if you lose two nodes in succession, and they just happen to be the two that are involved with holding your state data, then you're gonna lose it. But the odds, the odds of that are low, but not, what is it, Dumb and Dumber, where he says, so there's a chance. But it's extremely low that you'll lose two like that. Usually if you're losing two, you're gonna lose three, and you're gonna find out you just lost a switch or something, or your data center is going down. One is not uncommon. Two usually means there's something else going on.